lesions. And I can still remember the day that Aaron and I were sitting there, and he had run functional connectivity with some of these lesion locations, and we saw, boom, this anticorrelation to the extrastriate visual cortex. The exact spot of the brain involved in visual imagery just popped out. Moments where, I kind of couldn't believe that it was working, right? Yeah. Like when Ryan Darby first showed that lesions that cause delusions of familiarity, right, are connected to the familiarity detector, and they're all connected to our reality monitor. And like all of a sudden it was like, oh, for a century people have hypothesized this is a dual hit syndrome. There's been a lot of very, very exciting moments as we saw different lesion network mapping results and kind of put our hands behind it and said, wow, that's really cool.
Welcome to Stimulating Brains.
Mike Fox is the director of the Center for Brain Circuit Therapeutics, where he is also the Raymond D. Adams Distinguished Chair in Neurology at Brigham and Women's Hospital in Boston. A few years back, when Mike moved from the Beth Israel Deaconess Medical Center to the Brigham, the reason was to create exactly this Center for Brain Circuit Therapeutics, where the idea was to have colleagues from neurosurgery, neurology, psychiatry, and neuroradiology all under one roof, to work together and solve problems of neuromodulation in all types of brain disorders. I should probably mention that Mike recruited me to the center last year, so he is my boss and dear friend and dear colleague, and also one of my most important mentors. I owe a lot to him and have learned so much from him. So that's why I'm super excited to share this conversation I had with him about his work in resting state connectivity in the earlier phases, but more and more so on brain mapping using a connectome. In 2016, when I was a postdoc in Mike's lab, he once phrased it, we have the connectome now, so we have the map, but where do we go with it? And I think Mike is one of the few people that really has solved this question, especially with the aim of clinical translation, using the connectome to map functions and symptoms to brain networks with the aim of translation. He uses causal sources of inference, for example, brain lesions, TMS stimulation sites, or DBS electrode placements, to look at which networks map to which symptoms or functions in the brain. The aim here is to use these causal sources of information to create novel neuromodulation targets, both for invasive and also non-invasive neuromodulation. Our conversation was enriched by guest questions of former and present colleagues that I've worked with Mike, such as Shan Siddiqi, Aaron Boes, Michael Ferguson, Dan Corp, and Fred Schaper, and I'm super excited to be part of this community of brilliant minds that trained under Mike, and many of which have now begun to start their own labs worldwide in different places such as Utah or Finland or Germany. This is a growing community of people that are using these network mapping techniques to find out which neuromodulation targets are suitable to treat which symptom in the brain. So for me, Mike is really one of these very stimulating brains, and I'm pretty sure you're going to enjoy this conversation I had with him. Thanks for tuning in, Stimulating Brains. Okay, Mike, thanks so much for doing this. As you know, to break the ice before we get into science, I always ask about hobbies. So what do you do when not involved in science?
When not involved in science, well, I like recruiting very talented faculty members to my center. I don't know if that counts as a scientific hobby or not. But,
it still work. No.
As you know, I live on a lake. Absolutely love the outdoors. So paddleboarding, kayaking, playing with my kids either on the lake or in the pool. But no, my big pastime right now is being a dad. And then if I can be a dad outdoors, even better.
Great. I remember you once mentioned that as a kid you would go outdoors and find fish in the lakes, put them into your aquarium, and you were always an outdoor person, right?
Yeah, well, not just fish. It's whatever I could catch. Okay. Crawdads, turtles, frogs. I grew up in the woods, and the more I can get back to being in the woods. And now that I have a 7 and a 9-year-old, I have an excuse for catching crawdads and fish and turtles. And
Sounds great. So going into your career, science and medicine, who were key mentors and turning points?
Yeah, so certainly the dominant was my PhD mentor, Marc Raichle. He was my first scientific father, and just learned a massive amount from him. Obviously, I learned a lot about brain imaging, and just how to do science and write papers, but more, he continues to be my role model for how you run a lab, how you run a center, politically how you solve problems amongst different people in the lab, and I still remember going to a conference, and anytime Marc Raichle goes to a conference, he's like, I guess now, the grandfather, right? Walking through these imaging conferences where it's not just what he did with his own career, it's what all of his students did. Mm-hmm. And I'd say that's my model for where I want to go. And you train the best people, and that allows you to, one, let go of things and pivot and focus on something new. Yeah. So that's a real important lesson that he taught me. And then two, it's you see how science unfolds and how your efforts become multiplicative as people go off and do their own thing. And for me, that it was so salient, watching him walk through this conference, that stuck with me ever since, and it continues to be my career goal.
So essentially creating mini mics that would then pivot off and do their own thing?
No, that's the whole point, is that if it's a bunch of mini mics, then you failed, right? It can't be mini mics. It's got to be people that think differently than you. They learned something from you, right? You had an influence on them, but they think differently. They do different things. They do things that you never would have thought to do. Right, yeah. And so they're not mini mics. They're better than mini mics in important ways, and that's how you actually have influence on a field. So Marc Raichle taught me all that, and then obviously Alvaro Pascaleon, my postdoctoral mentor, really got me laser focused on translation, and always thinking about, all right, cool science is cool science, but what do you do with it? How do you take that science and translate that into, in the case of Alvaro, a neuromodulation intervention? Yeah. And so that obviously had a huge effect on how I think about things, and how you run a center and how you build a center focused on that goal.
Cool. And do you continue contact with both of them?
I do. Yeah, it's very important to me. I think a good mentor is a mentor forever, and they continue to have things that they can teach you.
Yeah, sounds great. So I will start with the first guest question by Shan Siddiqi about that first part of your professional life.
Hey, Shan Siddiqi here. So I've got two questions for this interview. First of all, where do you think you'd be right now if you'd never gone to medical school or grad school and you decided to continue being an engineer? What direction do you think your career would have gone?
Yeah, it's a good question. So at the time that I decided to give up electrical engineering and go to medical school, I did have a nice job offer on the table where I had worked for Procter & Gamble for a couple of summers. And I did not fit in with the corporate culture at P&G. And so their offer to me was, hey, we're launching this new initiative where we're going to take all the crazy people and stick them together in a building and hope they come up with creative things. And your job as the electrical engineer will be figuring out, can you manufacture any of these crazy things that people come up with? So every week you're going to be trying to build a new assembly line with a bunch of robotic arms doing different things, and so that's probably the job that I would have taken if I had not gone to medical school. Now, would I have stuck with that? Would I keep doing it? Would I have gotten bored of making diaper machines at some point? I don't know. But that was the job I probably would have taken if I said no to medical school.
Okay, sounds great. And I think you did then go to an MD PhD program in WashU, and you once said something like it's a good program for people that can't decide yet. So,
yeah, that's fair. No, it was true. I was very attracted to medical school. I was also very attracted to graduate school. I also liked being an engineer. But I think the MD PhD, it gave me at least me, I'm sure there are people out there that know what they want to do, but it gave me a low risk way to explore both options, and figuring that, all right, I'll push the decision down the line to some point and decide if I actually want to be a doctor or be a scientist.
Sounds great. So your earlier work with Marc Raichle that you just mentioned focused on, I think, a lot of things, but also anticorrelated networks in the human brain. So you were a pioneer in using and applying resting state functional connectivity, also developing it in the brain. Maybe we should start by briefly mentioning what resting state fMRI is opposed to task-based fMRI.
Yeah, sure. So, task-based fMRI is what a lot of people, I guess, used to think of as standard fMRI. I guess resting state has become pretty popular, but you can think of the standard preoperative mapping paradigm where you put somebody in a scanner, you have them tap their fingers, and you see what activates in response to the finger tapping.
Yeah.
And that identifies brain regions that activate during a certain task. And people use this task-based imaging for the early PET studies, for the early fMRI studies, and it was mapping out, what goes up when you do a particular task function. And then resting state was the idea that you could put someone in an fMRI scanner, not have them do any specific task, right? Just rest quietly in the scanner and try not to fall asleep, although it turns out that you can still see spontaneous activity when people are asleep or even under anesthesia. But you just look at these spontaneous fluctuations in the fMRI signal, and those are temporally correlated within connected brain regions and brain networks. And so it gave us a new way to map out not what makes this brain region go up or what activates this brain region, but what is the functional relationship between different brain regions.
And that was heavily influenced, or at least it was informative to have PET, which Marc Raichle worked before that, right? I think he used, would you say so? Or?
So it was motivated by a couple different things. One was just observation by Bharat Biswal way back in 1995, who just noticed, hey, there's a lot of spontaneous activity in this fMRI signal. Oh, look, it seems to be correlated between the left and right motor cortex.
Yeah.
Right? It was just something he saw, and it was an observation that sat out there for people to capitalize on, and eventually they did, and did big time. But I think for Marc, he came at it from a slightly different perspective. So, Bharat Biswal's finding had been sitting around for 10 years before, I or Marc Raichle ever got involved in the field. And I think what piqued Marc's interest was two things. One is Mike Gracious published a very nice resting state fMRI study showing the default mode network. And the reason that really raised our eyebrows is, one, we were interested in this network, but then two, it was in multiple different vascular distributions. So there was no way that could have emerged through vasomotion or respiration or cardiac pulsations or a lot of the artifact that people were worried about following the Biswal paper.
Yeah.
So the Gracious paper got us really interested. And then Marc had always come at the brain from a energetics and PET motivated perspective, which is what we see is that the brain is extremely active at rest.
Yeah.
And that when you actually do a task, you get this itty-bitty increase above and beyond this massive amount of ongoing resting activity.
Yeah.
And for Marc, his first insight into that was this default mode network, areas that go down when you do a task, right? Well, okay, if there's areas going down when they do a task, then they must be doing something at rest, right? And so then when this resting state fMRI came around, that was another reason to get interested in it, is this could be a window into the brain's enormous ongoing resting energy expenditure that you could see with these PET scans, and you could see based on regions that went down when you did a task.
So you're saying with PET you wouldn't be able to see that the default mode goes up during... Could you do that? Like, if in theory you could probably.
You could, yeah.
But it's easier with fMRI.
Right,
easier,
and then with PET you have the resting FDG scan. So just what brain regions are consuming the greatest amount of glucose at rest.
Yeah.
Right. So the FDG PET, was a resting state scan.
Yeah.
Right. Before they really had task activation mapping.
Makes sense. Super cool. So and then your landmark paper in PNAS from 2005, it was cited I think over 8,000 times by now. What did you find there, and why was it so important?
So first off, at least a third of those citations are saying that the paper's wrong. So if you do a controversial paper, you can accumulate citations. But I think most of the citations are that was the first paper where we kind of, if you will, put together the processing recipe for cleaning up resting state fMRI signals. So I mentioned, Bharat Biswal had a beautiful paper, Mike Gracious had a beautiful paper, and then when we tried to do it at WashU, we had a lot of trouble. Okay. In fact, I wasn't the first grad student that they assigned to the project. They had tried multiple times before I tried, And the problem was that the resting state signal does have neural activity in it, but it has those cardiac pulsations, respiratory artifact, movement artifact, and how you get rid of that wasn't trivial. And so for us, we had some resting state data. It was trial and error over the course of about a year and a half, where sitting down every night with Avi Snyder, trying different things, trying different algorithms, trying different combinations of regressing out different signals.
Yeah.
And then finally, we kind of developed a recipe that worked. And all of a sudden, these maps started popping out that just looked way cleaner than anything we had seen before. And so I think a lot of the citations of that paper are, that process of, regressing out the motion parameters, the temporal filtering, the global signal regression, but regressing out these covariates kind of led to a way to clean up the fMRI signal.
Yeah.
So that's part of it, is people just cite as a generic resting state fMRI paper. And then the other observation was this idea of the push-pull networks, these anti-correlations. And, yes, I am. I do realize anti-correlation is not a word. But we had multiple versions of the paper. We had the task-positive network and then the task-negative network. And we actually had a version where it was the task-positive network, task-negative network, and negative correlations. And it was just unreadable,
I see.
right?
Okay.
Because the positive negative was meaning multiple different things in different places, and so anti-correlation was stuck in there just to make the paper more readable.
Okay.
But for us, I think it was exciting because it suggests that these resting state fMRI maps told us something more than just what is anatomically connected.
Yeah.
It was telling us something about the polysynaptic functional relationships between regions. And over again with task, you saw that a certain set of regions went up, a different set of regions went down. And the idea that functional relationship that we saw over and over again in different task paradigms was there represented intrinsically in the pattern of the ongoing spontaneous activity. It really made us think differently about what these maps were showing us and what the maps are capable of telling us.
Yeah. And I would still say that sometimes there's criticism that fMRI hasn't taught us much about the brain yet, but I think that is one key thing, that the whole organizational architecture, that these massive networks ramp up and down and seem to stop each other, right? When one's active, it might have an intrinsic function of tuning down the other one, or
I think that's one possible interpretation of the data, but that's not proven yet. There's not direct inhibitory connections between these two circuits, and so I think all the fMRI signal really tells us is that when this one goes up, this one tends to go down. But it doesn't tell us the mechanism. It doesn't tell us how that happens. It doesn't tell us why that happens. But I do think it is helpful for mapping out the topography. It tells us where it happens.
Yeah, sounds great. Do you want to briefly tap into the global signal regression debate, or shall we skip that?
Well, the short answer is no. But I think it's for the listeners. I think it is useful as an example where everyone has to figure out what their balance is going to be between digging into the methods and just taking a method and running with it. And actually, before we ever published that paper, we had the follow-up paper on global signal regression fully written, right? We knew that it was an issue. We knew that it was a confound, and it was actually part of the original paper. The problem was it was going into a problem or a question that nobody was even asking.
Yeah, sure.
And it's very hard to answer a question that no one's asked yet.
Yeah. And
so Marc's advice, and it was, I think, accurate, was, let's just publish the paper. Someone will then ask the question. Mm-hmm. In fact, we would oftentimes talk about this issue in talks. And so then people started asking the question. Then we were ready with a follow-up paper to say, hey, here's our best set of analyses that go after, is this a real artifact, or is it something meaningful biologically? And then the field kind of did its own thing, where lots of different very smart people went after this. Is there a better replacement for global signal regression? Is it a confound? Is it a not confound? And I'm really glad that people dug into it, but it became such a debated methodological step that at one point people were getting their papers rejected solely because they either did this processing step or didn't do the processing step. And that was a very frustrating period of time. And actually, Kevin Murphy and I got together and wrote this, opinion piece on just trying to get a consensus of, hey, actually, we pretty much agree on everything here. These are just different ways to look at the data that are useful in different circumstances. And the analogy for neurologists I always give is nobody fights over how you montage the EEG.
Yeah.
Right? There are different ways to look at that EEG signal. The right way to look at it is the way that shows you the seizure.
Sure.
It's the same thing with resting state fMRI.
Yeah.
But I do think that it's great that there are people out there that really dig hardcore into the methods, and that's how we make the methods better and refine them better over time. That being said, if the whole field did that, then we would never be able to move forward and use any method for something useful.
Yeah.
So I think there's a balance there with any methodological debate.
Sounds great. But one thing I think that will be important for the next guest questions is that these anti-correlations or negative associations, negative functional connectivity values might tend to increase a bit if you do this global signal regression step. So it was a bit up for debate. Are these real? Are these physiologic, and so on? So I'm going to play two questions because they're quite similar, and you can maybe answer them together. So first is by Aaron Boes from Utah.
What do you think is the significance of anticorrelated networks in understanding human brain function?
And then the second one is from Michael Ferguson.
Hey Mike, it's Michael Ferguson. My question for you is, what finally convinced you that anti-correlated activity was a real physiological principle? And how did you feel?
All right. So both great questions, and so there's lots of ways I can answer Michael Ferguson's question.
Yeah.
And there's a development. We did a lot of analyses, and have published on a lot of them of different ways to look at the data and simulate the data and cut up the brain, and trying to convince ourselves that it's not all artifact, right? Do anticorrelations get a little stronger with global? Yeah, they definitely do. And so it's a question of degree. But to link the two questions very nicely, I'd say one of the best pieces of evidence that convinced me that the anticorrelations were real is when Aaron Boes developed lesion network mapping.
Yeah.
And so I still remember the day where Aaron and I were sitting there, and Aaron was trying to understand lesions that cause visual hallucinations.
Yeah.
And he had put together lots of cases of patients with peduncular hallucinosis, so a stroke in the brainstem or thalamus, that ended up having visual hallucinations. And it was very hard to understand how a stroke in these non-visual parts of the brain could result in hallucinations. And there, for a century, had been this long-standing theory of calling them release hallucinations, the idea that somehow the lesion is releasing activity in areas of the brain that are involved in visual imagery, and that leads to hallucinations. And I can still remember the day that Aaron and I were sitting there, and he had run functional connectivity with some of these lesion locations, and we saw, boom, this anti-correlation to the extrastriate visual cortex. The exact spot of the brain involved in visual imagery just popped out.
Yeah.
Right? And it made so much sense with so many long-standing theories of where these hallucinations must be coming from.
Yeah.
That kind of, that really hit me, right? That without these anti-correlations, there was no way to link up these lesion locations with the part of the brain that we were pretty sure was involved in visual imagery.
Yeah.
And then there's been
That's
lots of
great.
other pieces since that time.
Yeah.
But I think we had to switch to causal sources of information. So there's been lesion data that convinced me that there might be something there. There's been TMS and DBS data that's convinced me that there might be something there. But in all these cases, there's not a good way to link a causal site, a site of brain stimulation, or a lesion site with its effects on symptoms without taking into account the anticorrelations.
Yeah. Sounds great. So we will, of course, dive into lesion network mapping. I wanted to briefly, maybe, before we go into that, ask you, so after your MD PhD at WashU, you completed your residency in neurology at MGH, so Mass General Hospital. And I remember you recollecting a typical Boston residency anecdote once, where on a snowy day one would see medical residents on their skis coming down Beacon Hill to be punctual for rounds at MGH in the morning. So I just thought to pick your brain, because I rarely ask you that, any anecdotes from your residency time at MGH that you wanted to share? If not, we can skip to...
Oh, no, so many, but I got to pick a politically correct one. Sure. So one of the ones that I'll share is comes from when I was on the wards. My attending was Jeremy Schmauman at MGH. brilliant clinician and researcher. And I still remember we had seen a stroke in the emergency room. And it was somebody with a thalamic lesion, as I recall. And, as a neurologist, you go there, you do all your testing. It takes you 20 minutes or 40 minutes, depending on how comprehensive you want to be, to figure out, do they have a stroke? Where might the stroke be? Yeah. As you're waiting for the imaging to be collected. And I still remember, Jeremy Schmaumann comes down, pulls back the curtain, walks in, introduces himself. Hi, I'm Dr. Schmaumann. The patient reaches out, shakes his hand, introduces himself, and he turns around and leaves the room. And we're all kind of looking like, well, where are you going, right? He's like, oh, he's got a lesion in his left thalamus. It's a clumsy hand dysarthria syndrome. Huh. And literally within, 5 or 10 seconds, he had diagnosed, the syndrome, the exact location of the lesion, the patient's entire problem, and it just kind of blew me away of, wow, if I could ever be a neurologist like that, right? So that's just one anecdote that's
great. Yeah.
I remember.
Reminds me of the video challenges they sometimes have at the Movement Disorders Congress, where sometimes you see these cases where patients with movement disorders were not diagnosed for 10 years, but it takes that one guy looking at the video for 20 seconds and they know what it is, right? So that is sometimes super impressive for clinical practice. I totally agree. So great. After residency, you joined the BIDMC as an instructor, and there, of course, Alvaro Pascual-Leone was your postdoc mentor, and then one key method I think you developed in that time is called lesion network mapping, and you already tapped into it just now, but could you summarize a bit more generally what it is, what the idea is about?
Yeah, and I guess I just first want to mention, the before lesion network mapping actually was this idea of TMS network mapping. So I went over to Beth Israel to work with and learn from Alvaro, with the idea that with functional connectivity coming out of WashU, we had this tool for mapping out how different brain areas were related to one another. And I was definitely a tool builder in search of an app.
Yeah.
And so I spent my entire neurology residency thinking through, okay, we've got this great imaging technique that can tell us how different brain regions are related to one another. Where is that going to be useful?
Yeah.
And at the time, one of the big clinical problems was, where do you hold a TMS coil to help something like depression?
Yeah.
And there was evidence that TMS is working. Alvaro had done great work, along with Mark George and many others, showing that TMS could help depression, but it was administered using scalp measurements. And we said, all right, well, we know that TMS is having an effect not just at the stem site, but everything connected to that stem site. And it was kind of this perfect combination of, hey, I know a little bit about resting state functional connectivity. You know a lot about TMS.
Yeah.
Let's get together and see if this brain connectivity information can be useful for improving TMS therapy. So that was actually the reason I went to Beth Israel.
Makes sense. Yeah, absolutely.
And the reason I highlight that is because the lesion network mapping emerged fully from patient motivation and some degree of serendipity, right? Where Aaron Boes also came over to Beth Israel as a fellow to work with Alvaro and work with me, again, for TMS network mapping, right? Yeah. How do we combine brain connectivity to improve TMS therapies?
So maybe let's briefly talk about TMS network mapping before we go into lesions. So the idea there was that you want to hold the coil over a spot that's anticorrelated again to the subgenual, and I think that's your 2012 biopsych paper. Was that motivated by the DBS trials of subgenual, or?
100%, okay. Yeah. So I mentioned we had a tool for figuring out how different brain regions were related to one another. We had a clinical problem of where do we hold our TMS coil to try and improve depression. But then we needed another angle on it, another hook. And so Helen Mayberg's work showing how critical this limbic region, the subcallosal cingulate, was to depression was very influential. And at the time, she had recently published her papers, motivating implantation of DBS electrodes into that site. And I think you're hitting on something that is an important trend or focus of mine, which is how do you relate these different neuromodulation interventions to one another? I said, all right, it can't be a coincidence that we have a DBS target for depression and we have a TMS target for depression, and you can administer neuromodulation to either of these targets and make depression better. They got to be related to one another. And so it was Helen's work that motivated us to say, all right, we think the subcallosal cingulate is important for depression. We know that somewhere in the left prefrontal cortex is important for depression. How do they line up?
Yeah.
And so the 2012 paper was just a test of that hypothesis of, can we look at connectivity with this critical limbic region, and does that help identify topography in the frontal cortex that lines up with different TMS sites that seem like they're working or not working.
Super cool. And it seemed to work. And then I think one other landmark paper was your 2014 paper in PNAS, where you showed, again, more conceptually, but across, I think, 10 or 12 diseases, that the DBS sites and TMS sites would also, again, line up in the same way, right? So that is another really cool paper. Do you want to briefly...
Yeah, it was just the same idea. And again, it was, I had the privilege of, talking to Alvaro Pascaleon every day, and then he introduced me to Andres Lozano, one of the world's experts in DBS, and I had training in movement disorders and did DBS every day for Parkinson's disease, and so it was just this idea that we have DBS therapies that are effective for certain symptoms, we have TMS therapies that are effective for certain symptoms, and we've got an imaging tool that can link up different regions into networks. And can we test the hypothesis that our DBS sites that are working and our TMS sites that are working are part of the same network?
Yeah.
And if that's true, then maybe we need to be thinking about our targets for neuromodulation as brain network or brain circuit targets that are independent of whether you're targeting a subcortical node with DBS or a cortical node with TMS.
Yeah.
In the end, it's a circuit target. And so it was more of an idea paper. In fact, we had originally tried to publish that paper as just a perspective, right?
Yeah.
As a hypothesis or
Sure.
an idea. And it got rejected everywhere. And so then we tried to turn it into a quote unquote research paper.
Yeah.
But again, it got accepted and it got attention, not because the science in that paper is particularly good or rigorous. It's a concept that I think has proven to be useful as time's gone on.
Going into lesions now, finally.
We would get there eventually.
Aaron Boes came along.
Yeah.
What did he find? He had a patient, right?
Yeah, so it all started with a patient. So he literally saw a patient when he was a fellow over at Mass General in his pediatric neurology clinic, and this was a 16-year-old girl that came in with a peduncular hallucinosis syndrome. So, she driving her car, all of a sudden, was looking out her window, and boom, the whole countryside looked like it had been drawn in by crayon. Right, and as Aaron tells the story, and I think he actually wrote up her case report. She pulled her car over to the side of the road, looked at the passenger seat sitting next to her, and all of a sudden a bunch of flowers sprouted up from the passenger seat. Wow. And then she reached over to try and touch the flowers, and they all fell over. Right,
wow.
And so she told Aaron Boes this story in clinic. And he took a history, no psychiatric history, no reason to think this would be schizophrenia, a little young for that, and staffed the case with Vern Cavanis, right, one of the pioneers in neurology, and Vern said, I think she had a stroke. Mm-hmm. She's 16 years old, but sure enough she did. She had a lesion in her medial thalamus. But it was that patient that got Aaron really curious to say, okay, well, great, I read up on peduncular hallucinosis, I understand this is a thing, I understand that we see this, and we've seen this for 100 years, but I still don't understand why a lesion in these subcortical locations would be causing visual hallucinations. And so, he dug at it and dug at it and dug at it and just wasn't satisfied with the answer. And he had a very nice paper ready to go, just, kind of a comprehensive analysis of all the lesions that he could collate in the literature that had ever caused this syndrome. And then he just happened to knock on my door and say, hey, Mike, I hear you do some kind of brain connectivity stuff. Do you think that would be useful for understanding this patient's lesion? Mm-hmm. And that critical question, right, that Aaron asked, ended up launching this entire technique, because Aaron was onto something. He had the right idea, and it I think has proven useful for understanding peduncular hallucinosis, but for linking up lesions that cause a wide variety of different neurological and psychiatric symptoms.
Super, and we forgot to summarize what the general principle. So you have lesions causing the same symptom, and they don't overlap always, right? They can be always like everywhere in the brain.
Yeah.
And then,
Yeah, so I'd say there's two problems that Aaron ran into, right, that lesion network mapping was able to help solve. So one problem is the problem of heterogeneity in lesion location, where it's very, very common that lesions that cause a similar syndrome don't intersect the same brain region.
Yeah.
So in peduncular hallucinosis, all the lesions are in the brainstem and the thalamus, but they can be in lots of different locations in the brainstem and thalamus. Yeah. And so when Aaron looked at all these different lesion cases, there was a lot of heterogeneity. They didn't all intersect one spot. So that was problem number one, was heterogeneity in lesion location. But problem number two was, even if all the lesions did intersect one spot, let's say in the medial thalamus, that still doesn't tell you how the lesion's causing visual hallucinations. And
Not
that
connected to visual cortex.
exactly, and that gets to this dieschesis phenomenon,
Yeah.
right? That a lesion in any location has a functional effect on any brain region that's connected to that lesion location. So even if the lesions weren't heterogeneous, there would still be an extra step that could be needed to understand where the symptoms are coming from.
Okay.
And so lesion network mapping was the idea that, hey, we know that there's heterogeneity in lesion location. We know that there are dieschesis effects of the lesion on anything that lesion is connected to.
Yeah.
Do we have any tool that could tell us what that lesion location is connected to? And that's exactly what we did, right? Aaron looked at each lesion location. He then turned to a normative wiring diagram of the human brain, and it's important to emphasize that, right? We never scanned any of these patients with functional connectivity to see what the lesion was connected to, and in fact, if we had scanned the patient, it wouldn't have worked, right? Because the tissue at the lesion location is dead. It's not connected to anything anymore. So you go to a normative wiring diagram of the human brain collected from 1,000 healthy individuals, and it's an atlas that tells you what is this lesion location connected to. Now you do that for each lesion location, and that allows you to say, hey, do these lesions in different spots all line up? Are they all connected to anything in common? And then two, what is that? And it might be a brain region that's actually not lesioned by any of those lesions, because the symptom might emerge from a dieschesis-like effect.
Super cool. And that shows they all, so you find the common denominator, and then in that first paper already you mentioned that the anticorrelation seemed to be important because they would connect to the spot in the visual cortex. So all the lesions were anticorrelated to that spot. Is that correct?
Correct. Yeah.
Very nice. So what were maybe general challenges developing this method further? Do you have any, or also wins from the method? So what followed after that?
Yeah, so I think it's a good question. So the wins were easy. so it sort of became so Aaron, after he got his win with peduncular hallucinosis, I think we submitted that paper to a couple different places and it got rejected.
Okay.
And people weren't interested in just peduncular hallucinosis, right? Neurologists are interested in that, especially really nerdy neurologists like us, right? But they were interested in could this be a technique that holds true more generally. So even in that first paper, to get it accepted, we had to go through and show, hey, this isn't just a unique phenomenon that's only relevant to peduncular hallucinosis, that it might also be useful for subcortical aphasia, for pain, for auditory hallucinations, right? And Aaron put all those together and said, hey, look, this isn't just a one-off. This could be a general principle for how we understand strokes and focal effects of lesions and network effects of lesions. And Aaron was right. And so after he did that initial paper, it was almost off to the races. And then it just became any fellow or resident that knocked on my door, I was like, all right, what are you interested in? I'm interested in hemichorea. All right, go for it. Map out lesions. Great. And so and then I started to get fellows knocking on my door with totally crazy ideas. And, Ryan Darby knocking on my door would be like, I'm interested in Capgras syndrome. Can it solve the Capgras syndrome? I was like, well, probably not, but give it a try. And then it was just shocking where it just kept working. And it wasn't like, it worked half the time. We don't have a whole bunch of skeletons in our closet where it's, we tried it in all these different syndromes and we got absolutely nothing. It just kept working. And so I think Aaron just stumbled upon a fundamental principle of how the brain works and how symptoms localize. And they don't localize to regions, they just localize really well to networks. And this resting state connectivity, because it's polysynaptic, because it reveals functional relationships, ended up being a good way to map these things out. And then I think the challenges that you asked about, anytime there's a new method, it gets to this debate of the processing algorithm for resting state data.
Sure.
There are many different ways you can do this. Do you take the peak sites of lesion intersection and run that as a seed, or do you run each lesion location as a seed? And actually, that was a debate Aaron Boes and I had for that first paper, and it remains an ongoing debate.
Okay.
In some of his recent papers, he's done things that way. There's a debate of, is functional connectivity the way to do it, or is anatomical connectivity a more useful way to map lesions onto networks and onto circuits? And are there different symptoms where anatomical connectivity might be better than functional connectivity? So I think there's a lot of ongoing good methodological debate and development to figure out how we optimize the technique. But I think the general principle that lesions causing the same symptom map onto a network or a circuit is holding true.
Seems to work, yeah, definitely. So how did it feel once you realized this? It probably took a few years, right? Get the first papers out, but at some point you realized, hey, this really seems to work. What was that feeling like? Probably wasn't it?
There was never a moment,
yeah,
right?
Yeah,
it's cumulative, and I wouldn't say, even now, I'd say, I'm now confident it works, right? I keep looking for that example where it fails, right? And I would say that there were definitely moments where I kind of couldn't believe that it was working, right?
Yeah.
Like when Ryan Darby first showed that lesions that cause delusions of familiarity, right, are connected to the familiarity detector, and they're all connected to our reality monitor. And like all of a sudden it was like, oh, for a century people have hypothesized this is a dual hit syndrome. Like the lesion must be doing two things and disrupting two different processes to cause this very amazing delusion of familiarity. And it was like, okay, sure enough, the lesion's connected to two different things and two different networks. And
feels too good to be true.
Yeah, exactly. It's one of those things where it just makes, I don't know, I do believe in science that things that are true feel simple in retrospect. And again, it just was like it made so much sense.
Sure.
And so I do think that each time we study a new syndrome and a complex syndrome, and things all of a sudden make sense, it just continues to amaze me, right? That we have a tool that can even begin to study some of these more complex things. We have papers on free will and criminality, just things that religion, right? That you can barely even make these topics accessible to neuroscience in general with any technique. And the idea that I happen to have a tool that allows me to address these fascinating questions that go beyond neuroscience or direct patient care is super fun.
Super cool. Yeah, very, very nice. I remember loosely that you were at the time in this beginning phase collaborating strongly with methods people like Hesheng Liu, Randy Buckner, Tom Yo. Was that important to get the setup and the connectome running, or would you think in general your network mattered a lot at that point to get this running?
Oh, 100%. Yeah, no, I one of my general principles is to try to always find someone smarter than me and then partner with them and collaborate with them. Yeah. And certainly at that period in time, that group that you mentioned was so helpful in so many ways, where I had just come in from WashU. I was spending most of my time being a resident, right? And so I only had time for science on the nights and weekends. And I certainly didn't have time to, rewrite all the WashU code to work with, the system in Boston.
Yeah.
Right? And so just even the format of the imaging files and the, the resting state data sets and, all that was different. Sure. M&I space was not a thing at WashU.
Oh, really?
Right?
Okay.
Nifty files were not a thing at WashU.
I know, yeah.
And luckily, Randy Buckner had moved from WashU to Boston just about 5 years or so prior to me, and had already solved all these problems. So having Randy as a mentor, I would have been, he basically allowed me to accelerate my entire research portfolio by 5 to 10 years, because he had already solved so many of these problems. And then, in his lab and collaborating with him were Thomas Yo and Hesheng Liu, and they were very generous with their time and their expertise to help get some of these things working. And so, it was really the right group of people at the right time that helped me tremendously.
So you mapped since then quite a bunch of symptoms, as you mentioned a few. So 7 years after this first paper now, you wrote just recently a review together with Juho Jutsa and Dan Corp, who both postdocs with you at some point. And I think it includes a more or less exhaustive table at the time, currently, of symptoms and functions mapped with the technique. I'm just going to read a few of them, not all of them. Addiction, akinetic mutism, alien limb, aphasia, amnesia, anosognosia, for hemiplegia, autoscopic, my German accent is too terrible, blindsight, bodiless awareness disorders, bodily self-confidence, and so on. Coma, criminality, central hyperventilation syndrome.
Alphabetical.
Exactly. I wanted to make the point. I just made it to the third letter, and I even skipped a few now. So lots of symptoms have been mapped. Why do you think is the technique so powerful and also now popular?
So I'd like to believe that it works so well because we stumbled upon a fundamental principle of how lesions cause symptoms, and we just happened to have a tool at our disposal that is very, very useful for understanding lesions and lesion effects and relating lesions to one another.
Yeah.
So I want to believe that is why it has worked across so many different neurological and psychiatric symptoms.
Yeah.
Right. I would say there's a skeptical side, which, and a concern that I will continue to harbor, because you always got to be very skeptical of your own stuff, and the skeptical side is to say, oh well, it has worked and it's gotten popular because it's super easy with a very low bar, right? Mm-hmm. Where all you have to do is search for case reports of lesions causing fill in the blank, right? Copy those lesion locations onto an atlas, take a publicly available connectome, right, which anybody can download, and then you just take the lesions, run them as seeds, right? So you can run a lesion network mapping study in, 3 months, 6 months?
Yeah.
And so it's a very low bar to go in and study an interesting symptom. Well, that creates a danger, right? Sure. And so it's going to gain popularity because it's easy to use and apply.
Yeah.
But it also comes with a lot of risk that, because it's easy to use and easy to apply, maybe people have done 20 times these number of conditions, and then through publication bias, we just don't even know about the times where it doesn't work, right? There are probably instances where people are applying the technique to things that it shouldn't be applied to.
Yeah.
And it's funny, reading that off that table actually reminds me of a review article I did with Marc Raichle early in the days of resting state functional connectivity, where we did this ridiculous table of all the disorders where resting state functional connectivity had been applied.
Oh,
right?
Interesting.
And in that review article, we actually made the point that it's being applied to too many things, right? And that it can't be possible that all of these are, disorders of resting state connectivity in the default mode network. And so, I think it's great when a new technique is developed. I think it's great when it's widely applied. But when it does get applied that broadly, you do wonder, should it be applied that broadly? And is this just a fundamentally valuable way for mapping out different symptoms? Or is it being over-applied because it's just easy to do with a low barrier to entry? And I'd say time would tell. I think, we haven't yet done the prognostic, prospective study of, do any of these lesion networks actually predict which lesion patients are going to develop these symptoms? And those studies are ongoing. But I think that the prognostic value of lesion network mapping will be a real important test of, does this hold water? And then there's a lot of therapeutic targets or possible therapeutic targets that have come out of these lesion network mapping studies, and those are all testable hypotheses.
That's the perfect segue into the next guest question, again by Aaron Boes. Let's hear that one.
Of all the lesion network mapping studies that you've worked on, which do you think has the most promise for a novel therapeutic target?
Yeah, great question. So I'd say, that one's, the front runner in my mind is definitely addiction. We've studied mostly lesions that cause a symptom, right? You can map it onto a network, but there's now a conceptual leap to say, all right, that network for lesions that cause a symptom, is that the network you need to target to make the symptom better? Because it might be, but it might not be, right? It might be you have to target a different network that helps you compensate for that symptom. But then a very small number of symptoms, we study lesions that get rid of a symptom. So lesions that get rid of tremor, map onto a brain circuit that exactly highlights the VIM nucleus of the thalamus, which is our DBS target for tremor.
Yeah.
And then the next one that Juho Jutsa did was lesions that get rid of addiction. And because it's lesions that improve a symptom, you don't have that conceptual leap,
Sure.
right? This is the connectivity profile of a lesion that gets rid of addiction.
Yeah.
So where are the spots in the brain that best match that connectivity profile? In theory, that's where you should put a lesion to get rid of addiction.
Yeah.
And so, we have a spot near the anterior cingulate that comes out, which is a classic lesion target for addiction.
Yeah.
We have a spot in the anterior insula and the frontal operculum that comes out. That's a classic, the insula, I guess, is a lesion-based target for addiction. Nobody's actually lesioned the insula that I'm aware of. But we do have a couple spots where I'd say if those spots fail, if you lesion those spots and they fail to help addiction, that would be a pretty direct challenge to the therapeutic value of lesion network mapping.
Makes sense. Okay. And then if you would want to go one step in between before lesioning, you could also apply non-invasive stimulation, for example, TMS and TDCS. Would you say the same applies there, that the lesions that cause to loss of a symptom or improvement of a symptom would be better for that, or would you say there is different? Because
so it's the challenge, and that's why I said if you put a lesion there, that's the best test of the hypothesis, right?
Sure.
And the challenge with different non-invasive technologies is that they're not really a lesion, right? So people talk about TMS as a virtual lesion, but it's really not, right? And even DBS, right? We think of DBS sort of like a lesion if you administer at high frequency, but really that's just because through trial and error, it kind of seems like it acts like a lesion in certain movement disorders.
Yeah.
And so it's very possible that it is the right therapeutic target, that a lesion could work really well at that location, but that TMS to that spot or focus ultrasound to that spot or DBS to that spot might not work.
Yeah.
Now that might be the right next step, right? Certainly for, lesion therapies, there needs to be a very high bar before you go in and start lesioning patients. But that is scientifically the best test of the hypothesis.
Yeah, makes sense. That's very makes a lot of sense. Great points. So I think all of these symptoms, or many of these symptoms, led to an invited review that you wrote for the New England Journal of Medicine in 2018, which also shows, I think, the big impact and interest in this technique. From all these symptoms and functions that you've studied, do you have a favorite one? Just, personal favorite?
Yeah, I'd have to think about that one if I had to choose a favorite. There's been a lot of very, very exciting moments as we saw different lesion network mapping results and kind of put our hands behind our heads and said, wow, that's really cool. I think, going back to that story I told earlier, like the day Ryan Darby, quote unquote, solved the capgras delusion, right? That one to me was, that was really cool.
Super cool story.
It's hard to know if it's right, but it makes a lot of sense.
Let's go with that. So what one key point that you recently also highlighted together with Shan Siddiqi in a review paper is that, and you mentioned it before, that the lesions introduce a causal modification to the brain, right? You have a stroke and then something changes. It's a causal intervention. There are other causal interventions, and namely, I would say, brain stimulation, as you point out. So deep brain stimulation and TMS and other forms of neuromodulation are other forms of causal intervention. And your lab has combined all three of these in some papers, sometimes two of these in sources of information. Can you talk a little bit about that? What's the importance of these causal ways?
And so that's I got to give a very nice lecture at the Organization for Human Brain Mapping a few years ago, and it was thinking what is the message that I want to give to all the neuroimagers out there, and it was very clear, which is, we need to rethink neuroimaging. We've been doing neuroimaging for 3 or 4 decades, looking at, imaging correlates of these symptoms we want to treat. But our track record of translating those imaging correlates of symptoms into newer effective treatments is not good.
Yeah.
And why is that? It might be, we're just not there yet, and it has to evolve over time, and that's the standard answer. Or it might be that fundamentally there's something wrong with this approach. And and I'm not the only one to worry about this, right? It's kind of emerged as this idea of the causality gap. where you can have an imaging correlate, but that doesn't mean that that's an effective therapeutic target. And so if we believe that that's a problem, then how do we close that causality gap? And one way to close it is through what I'll call the causality opportunity. It's to focus on causal sources of information for mapping out symptoms. And brain lesions is our original one. And in fact, brain lesions and these incidental observations of lesions doing different things led to many of our effective neuromodulation targets. And so lesion-based localization actually has a very good track record for turning into effective treatments compared to neuroimaging correlates. So, all right, let's double down on the path that's working and maybe deviate a little bit from the path that's popular. And so we focused all in on lesions as the dominant causal source of information, followed by DBS electrode locations or TMS stimulation sites, with the idea that you can map things out based on one causal source of information, and that should be valuable. But if you can actually do convergent causal mapping, if you can map out the circuit based on lesions, map out the circuit based on DBS effects, and map out the circuit based on TMS effects, and these three causal sources of information all converge on the same brain circuit, well, now you got a really strong case that this circuit is causally linked to this symptom in humans, and modulating this circuit causally leads to a change in that symptom. That's as strong as you can get as your candidate therapeutic target. And that's what Shan Siddiqi did recently for depression.
Just wanted to say that's probably the canonical study so far, right? That can you summarize what he did in that study?
Yeah, so he took 5 lesion data sets where they did depression scores after the stroke, and then he took roughly 5 DBS data sets and 5 TMS data sets. Where in the DBS data sets they measured depression scores before and after DBS, TMS same thing, depression scores before and after TMS. And in each one of these cases he mapped out what the lesion, the DBS site, or the TMS site was connected to. And then asked, okay, which connections covary with depression score or change in depression score? And so you can map out a lesion-based depression circuit, a DBS-based depression circuit, and a TMS-based depression circuit, and just ask, do these 3 things line up? And they did. They lined up really well. That's another one of those moments where I remember Shan popping those 3 maps up on the screen and just looking at me like, no, this can't be real.
That's great.
But yeah, no, I think it was the best and the most rigorous test yet of this idea that lesions and brain stimulation sites or TMS sites and DBS sites are all going to converge at the circuit level, and that resting state connectivity might be a useful tool for testing whether these things converge at the circuit level.
And I mean, we can even say, I think in that study, that the DBS sites were not all in depression, right? They were somewhere in epilepsy, somewhere in Parkinson's disease. So you even have some cross disease symptom mapping in that paper as well. So I think it's a really landmark paper, really great work there. I think the next guest question, again by Aaron, will I don't know if you have a spontaneous answer to that. Maybe you have to think about it a bit, but we'll see.
What do you envision lesion studies will look like 50 years from now?
Yeah, it's a great question. I think everything's moving towards big data and big lesion collections, and Aaron Boes being at Iowa is just such a beautiful thing, because Iowa's got this rich history of really collecting lesion cases and studying and phenotyping lesion cases, and Aaron has kind of revitalized that at Iowa, and you build big ends. The Discovery lesion cohort being run by Natalia Roast over at MGH. The goal is to collect 8,000 lesions, 6,000 of which will be focal strokes, and phenotyping all these patients. And so I think it'll move towards, a lot of our lesion papers now are 30 lesions that cause this thing. Well, 6,000 lesions, right, is a different level of power. Now, they won't be as clean phenotypically. One of the things that's been nice about lesion network mapping is these case reports of this really clean phenotype that somebody was motivated to write up have been just worth their weight in gold. So I'll answer it 2 ways. I think one is moving towards big data. Huge lesion data sets where we've got depression scores, memory scores, you name it. And I think that those efforts are happening. But I think the other effort that has to happen, and I'm not sure how to put some motivation behind it, is doubling down on these incidental cases that just have these very clean, striking phenotypes. Where you see the case and it's like, wow, right?
Yeah.
The lesion did that. And right now I don't know that we have a great way to capture those very important and interesting lesion cases they're not subtle changes in depression score, but just that striking phenotype where the lesion either caused a severe depression in somebody with no history of psychiatric illness or got rid of depression in somebody with a big history of psychiatric illness. And right now those cases are happening. I'm convinced that they're happening. And if you could find a way to collate the world's database of stroke, all the stroke cases in China and India and all the different institutions in the U.S., I think if you could capitalize on that in some way, you would be leveraging serendipity towards therapeutic targets at scale.
Yeah.
And so I'd say that's the other thing that I'd like to see happen in the next 50 years of lesion studies.
Sounds great. I very much share that vision. Very cool. I think the podcast, as you know, is about the brain simulation mainly, or brain stimulation. So we've talked a lot about lesions, and they have a great value for informing both invasive and non-invasive brain stimulation targets. But you also clinically and scientifically are very much involved in the brain simulation. So are there, maybe in parallel to what Aaron asked, any key highlights you foresee for the future in that field?
Just in DBS or TMS, or
both of them, but maybe DBS.
Yeah, it's a great question. So it's an area of rapid development. Your podcast has covered those developments across brilliant speed. By the way, I'll take a moment to say I love this podcast, and I love all the speakers you've had, and it is an absolute privilege to be interviewed given the set of people that you've interviewed so far. So you've well documented a lot of different visions of where DBS is going. And I'm trying to think if I have anything actually useful to add or complement what all the other speakers have said about DBS.
My follow-up question would be, what do you think about closed-loop deep brain stimulation?
Yeah,
you want to talk about?
Yeah, and I'm excited about it as an electrical engineer. It's the super duper cool, right? I think I'll mention a couple things to complement what other people on this podcast have said previously. So one is there's a lot of development in the DBS area that I think is driven by very cool engineering and the ability to do cool things with our engineering, and maybe a little bit less by patient need, right? I believe fundamentally in the clinician-scientist model, and doing DBS clinically really tells me what the problems are, right? And the problems are balance, the problems are freezing, the problems are speech side effects, right? And some of those problems can be addressed with closed loop or adaptive design, but some of them maybe not so much, right? And so I think for me, I spent a lot of time thinking about stimulation site and symptom-specific circuits and side effect circuits, and so I think one is can we change the location of stimulation slightly to better avoid a side effect like cognitive decline in ST and DBS or Parkinson's disease, or maybe even have some benefit on gait or balance or freezing. Now, not with our traditional target that improves tremor or improves rigidity. It's going to be a different circuit target, but it doesn't mean that there's not some circuit that we could reach with flipping on a different contact that could have a symptomatic benefit on some of these things that right now we feel like can't respond to DBS. Or even the psychiatric side effects. It's very common that we'll have a patient with psychiatric issues, depression, anxiety, and they want to know, is can you do anything about this with my DBS electrode? And right now we say no, but that doesn't mean we can't, that just means we don't know how to do it yet. So I do think it's moving towards this idea of symptom-specific circuits, of reprogramming trials, of flipping on other contacts in different ways that might help different symptoms. And then the other one that I'll mention, just because you already know what I think about closed loop, but I like being controversial and telling people that one future of DBS is extremely cool engineering and fancy devices and closed loop designs with sensing all over the brain and stimulating in different areas of the brain. And the other future of DBS is just burning a hole and
Yeah.
going back to lesions.
Yeah.
And that again just came from my patients, where as focused ultrasound became an option, I would see patients over and over again where they would, see somebody for a focused ultrasound intervention, they'd see me for DBS. Both of us would tell them that DBS is better, and it can give you better tremor benefit with fewer side effects. And time again, the patients were opting for the lesion. And it just kind of blew my mind. And then it suddenly dawned on me that patients don't really want a fancy piece of engineering in their head if they can avoid it. And the idea that they could do one and done might be preferable for certain patients, certain symptoms, certain conditions, especially as we start moving into psychiatric symptoms. So my controversial take on it is that DBS is just a stepping stone to figure out exactly where those symptom-specific circuits are and the exact spot in the brain that we need to modulate to have our benefit without side effects. But once you know that exact spot, burning a small hole there, if you can be confident that it has the effect, might actually be the future.
And I guess it's two things, right? It's knowing exactly where it's a lesion, but also being able to, as precisely as possible, lesion there, right? And I love the idea, the idea that the MR-guided focused ultrasound happens in the MRI, because even if it's not perfect yet, I think that technology will have the possibility to see exactly where your lesion, right, in anatomical coordinates and so on. So some more. So I know that you're working on the concept of the return of the lesion, and I think in that you propose that after lesions had a break over history, to some degree, they are now celebrating a comeback, and not only for therapeutics but also for diagnostics.
The broader principle that I think is important for me and maybe for your listeners is, where have our successes come from, right? And right now it's we're trying to build a center, right? And the whole goal is new treatments, right? And academia, you're motivated by papers, you're motivated by grants, but the goal really needs to be treatments, right? And so it's spending a lot of time thinking about where have our successes come from, where have our wins come from, and how do we learn from that, leverage it, improve upon it. And lesions have such a strong history and such a strong track record that going back to lesion-based localization has value. And then, and again, it's controversial, right? But to say that lesions might be a future neuromodulation intervention, is worth thinking about. It's what is going to be that disruptive technology. It also, I think, hits on one other point that's useful to make, which is I've spent a lot of time in my career watching where the herd is going and intentionally going in a different direction. And the reason is that if the herd's already going there, the world doesn't need me in that realm. And so you mentioned, closed loop and adaptive DBS. The people working on that are some of the smartest people that I've ever met, right? You go to DBS think tank, you're just blown away by what people are doing with the engineering, the electrophysiology. And so they don't need me there, right? Like I'm not smart enough to compete in that space. Sure. And so it's okay, what are they not doing or not thinking about? Or when I came out of residency, I went into residency being someone really focused on resting state connectivity. Right? Well, I came out of residency and there was a whole army of people working on developing resting state connectivity. They didn't need me there. And so right now with therapeutics, it's the same way, right? If adaptive and closed loop designs are going to get us there, we're going to get there. So for me, it's what is the area that's not being explored where I could potentially add value. And I like it as a principle because I think the more heterogeneity we have in science, the more people pursuing different ideas, different options, crazy avenues, the faster we actually get to effective treatments, and that's everybody's goal.
Sounds great. Great concept and teaching point. So the serendipity story was actually the next question I wanted to pick your brain on. You already summarized it, but I think it's worth to mention a bit further that I think it's motivated by Marwan Haris's recent, or at least that was one paper that you really liked in that realm, where he made the point that looking back at history, there's not so many wins as one would think from, coming from the animal research model, where we usually think, we have a mouse model, we study something in the brain, and then we derive a therapeutic target from that for neuroscience. And looking back, there's just not so many wins in that. There are some, but not so many. But there are a lot of wins in the just looking at case reports or looking at variations and interventions. Do you have thoughts on how we could capitalize on that further?
Yeah. This was the think tank, right?
Yeah.
I kind of proposed that, so serendipity and the role of serendipity is something that I've loved for a long time. I was just so excited to see Marwan's article where he did the hard work of putting together the history, which I don't know, right? I'm not a historian. It's actually one of the reasons I love the podcast so much is I get the history that I wish I would have gotten from having all of these people as my mentor, right? That they could tell me the history. And so it's trying to learn from that history. And one of the things that you've pointed out is, functional neuroimaging correlates don't have a great track record of turning into new treatments. Mouse models of human brain diseases don't have a great track record of translating into new treatments. So what does have a good track record? Or are we just doomed to failure no matter what avenue we pursue? And again, that's the trial and error in human patients, right? And it sounds brutal, and it sounds very non-scientific, and maybe even non-ethical. But that is the history of our wins. That's where our successful treatments came from. It was the incidental observation of James Parkinson's patient number 6 had a stroke and the tremor stopped. So what did we do? We started lesioning and creating strokes all over the place, right? Trying to get tremor to stop, right? And eventually, we had trial and error success where, people went in, tried to lesion one thing, had a bleed somewhere else. Suddenly somebody's tremor stopped and they weren't paralyzed. Okay, huge win. But it was these trial and error interventions on human patients with careful observers as to what was working and what was not working, taking full advantage of the heterogeneity in their outcomes, and then refining their treatment over time until they converged on something that worked with minimal side effects. And so that pathway that worked very, very well in movement disorders, how do you apply that elsewhere? And so I look at, we recently had the paper on addiction. So there were a bunch of lesion treatments for addiction happening in China, happening in India, right? And they got shut down, and maybe for very good reasons. I don't know the history, but there were ethical concerns, there were side effect concerns. But those lesions are now all lost to the dustbin of history, and I know I tried to get them, right? But they weren't recorded in a systematic way. People didn't look at the heterogeneity, what worked, what didn't work. Oh, here's an incidental case where I actually was aiming for the anterior cingulate and I missed, and I got this other spot. Well, did it work better? Did it work worse? And so I think you had the people developing therapies for movement disorders that were leveraging the heterogeneity in their outcomes. They were embracing serendipity. They were studying it, right? And they had lesion therapies in probably the same number of cases for addiction where they weren't taking that same approach, or at least not in a way that I've been able to access. And so to me, you can learn from that history, learn from where the wins came from. And when I talk on, how do we go all in on leveraging serendipity, which was a controversial question to even pose at think tank, because by definition, you can't plan for or leverage serendipity, but maybe you can. And so it's
and you had some ideas on how to.
Or just it's any time you intervene on a human brain, right? Especially with some type of causal intervention, whether that be a lesion, a DBS electrode, a TMS site, right? To give you an example, I listened to Josh Gordon's interview, right? And the NIMH has done a really good job of essentially mandating certain things, and it moves the entire field, right? So they mandated that they want some imaging biomarker of any intervention for a mental health disorder, right? Well, what if you mandated that any DBS trial has to publish their electrode locations? Any TMS trial has to record the exact site of stimulation, right? That's a way that you plan for serendipity and you leverage it, right? Because now you start building here's what worked, here's what didn't work, here's had this unusual effect or didn't, and then people can mine that and begin to back out and converge on, a target that might be even more effective. That was just because you got the electrode in the wrong spot.
Love the idea, right? So to make that mandatory, that would be great for everybody, right? And I think everybody would love it, right? If everybody shares their sites, that would be super. I think the other thing you once mentioned would be if we have a really informative case report, it's usually there's no good journal for that, right? Or it's not valued as much as a big paper. So that could be another option, I think.
Yeah. Well, I mean, as we were brainstorming the other day, it would be amazing to have a registry of causal case reports. So a lesion, a DBS stimulation site, a TMS site, right, where you have the causal site of intervention, and then you have the interesting behavioral phenomenon that occurred after that. And if you could create, maybe publishing each one of these case reports in a paid, journal is not the way forward.
Yeah.
But if you had an online registry of these cases that became a PubMed indexed or citable element, where now residents can just submit their interesting cases, right?
Yeah.
And eventually you start accumulating enough cases that people can make sense of different lesion locations that did something or DBS sites that did something. Could be a cool model.
Love the idea, and so on. So I have one more question in that direction before we move on to some more general questions by somebody in Australia. So,
hi, Mike and Andy. Mike, my question is, who is your favourite Australian postdoc of all time? And don't answer that if you've had another one other than me. No, my real question is, what do you think of companies like Neuralink? I'm sure that you've been asked this a lot, but I've never heard your thoughts on it. Do you think that these companies are the future and that they can really help people with brain disorders? Or is the human brain just too complex? Thank you, and I hope to see you both soon in person.
So thanks, Dan Corp. Great to hear from you. And then with the thick Australian accent, I'd also want to know what the company Neuralink is. So is that a popsicle company or a lot? No. So the question about Neuralink, and is it a good thing? Is it a bad thing? I think any investment of resources into a important field is a good thing.
Yeah.
And that company, with Elon Musk, brought in a huge amount of money into the field, a huge amount of PR and interest in the field, and that's almost always a good thing. It'll spur development. It'll spur other companies to be interested. VC will be interested. Other scientists, that are thinking about what they want to do with their life will get interested. Yeah. And so I think it's a good thing overall. Now, whether or not neuromodulation to enhance function, which is, I don't know, Neuralink has changed their PR over time. Yeah. Right now, they're right now focused on treating brain disease, but at one point, I think that they were focused on neuroenhancement, and they're not alone, right? There are a lot of other neuromodulation device companies out there that are focused on neuroenhancement, and that one I'm not sure whether it's really possible or not. Millions of years of evolution have tuned up our brains to work pretty well.
Yeah.
And my guess is that we can enhance certain functions. It'll be at the detriment of others.
Yeah.
And the idea would be you enhance certain things at certain times where it's advantageous to you, and then enhance other things at other times. So I guess one is just, is it even possible to do neuroenhancement? I'd say maybe, but it's not an easy bar to overcome. Most of our brains are pretty good at what they need to do. And there's always a risk of unexpected consequences of trying to make something that works pretty well better.
Yeah.
But let's just say we can overcome that hurdle and neuroenhancement becomes a thing. I'm not fundamentally against it. It just comes with a large set of other problems that will then need to be solved of, equal access and how do you prevent the smart from getting smarter,
yeah.
right? And then other people that don't have access to that technology fall even further behind. And,
yeah.
But in general, you don't really stop technical advancement.
Yeah.
I'd say the only area where we think it's actually been paused is, the field of human cloning and human genetic engineering, where technically we have the ability to do it, and for ethical reasons, it really has put a pause on that area of science. Yeah. But neuroenhancement, despite the ethical concerns, I think that, if it works, people will develop the technology, and it's almost a, fighting that I won't say it's inevitable, but it almost sometimes feels inevitable. The technology will advance. If it can be done, it will be done. And then only in retrospect can we have the fight over whether it should have been done.
Yeah. So I'm gonna move to some more general questions, and one is hard to fit into the narrative, but I think it's a great question by Shan. I am going to play that now.
And my second question is, who do you think would win if all of the people who you've ever mentored were in a Royal Rumble fight to the death? And obviously you can't choose Joe Taylor because he's the best fighter out of all of us, so he would obviously win, so he can't be in this. And I know the right answer. I'm going to give you a second to think about it.
Oh my goodness, I continue to find out that, you know, people that I am mentoring are very skilled in the martial arts in ways that I am not aware of, and you know, and so now I'm trying to figure out. He's clearly thinking of someone other than Joe, and so that means there's someone else that I mentored that's very, very skilled in martial arts, and I have to think of who it is now.
It's not that. It's not that.
Oh, it's not that. Okay. Well, then I don't know.
But who would you pick? He wants to know who you would pick. Who would win?
Who would win in Royal Rumble with everybody I've ever mentored, and I can't choose Joe Taylor. Who, for anybody who hasn't met Joe, is very large and very skilled in martial arts, I believe. Let's see. I think I didn't mentor him, and we're collaborating with Hisheng Liu. Was actually a kickboxing champion in China.
Oh wow!
And so actually, Hisheng versus Joe would be a good rumble. but I think if Hisheng showed up, I would probably put my money on him. Especially I can't put it on Joe. But I want to hear what Shan thinks. He clearly thinks he knows the answer.
Yeah. Obviously, the right answer is Alex Cohen, because he'd figure out a way to turn everybody against each other, maybe some clever algorithm or something, so that he can step back and wait till just the right time to step in when everybody else has damaged each other to the point of no return. But I'm curious to hear what your wrong answer is.
All right, I wouldn't have come up with that answer. So, but he is right. Alex Cohen is extremely, extremely smart. I would say Alex Cohen might win simply because he would be so good at collaborating with everybody else that nobody would possibly risk losing Alex as the collaborator. And then but I think Alex would be a good choice because he's so good at working with everybody else.
Great. Speaking about general scientific questions or like general questions, so I always ask about eureka moments in science, and I think we have already covered a few of them. But even maybe thinking back to your earlier days, or do you have any other like great moments to share? And could also be just wins or lucky streaks or whatever.
Yeah, there's been a lot of them. I mean, I absolutely love this job, and I love being able to do the programming and write a new algorithm. And I still remember the first time that we threw in global signal regression into the resting state connectivity algorithm. Right after pounding on it for a year and a half, all of a sudden these maps popped out, and it was just like, oh my God, that's beautiful! It's so much prettier than anything we've seen. Right? I still remember how exciting it was that night. Right? It was probably 2 a.m. with Avi Snyder, right? And then, and I still remember sitting there with Aaron Boes the first time we looked at the connectivity of these lesions causing hallucinations. Like, oh my gosh, like this could be really important. Yeah. And so there's been a lot of them, and I continue to have one. It was a couple weeks ago, right, where we sat down. It was lesions causing anorexia, and it was like, oh my gosh, that makes a lot of sense. So look for that one to come out. But but no, there's definitely been a lot of times where it's like, wow, that's super cool.
Yeah, great. I was lucky to witness some of them over the years. So it's been a great ride. I agree. So we also should always talk about failures. So or missed opportunities or waste of your time. Any things you want to share in that?
Oh, yeah, that's a good one. So the short answer is no. And the reason being is I don't believe in failure in the sense that there's a lot of things that don't result in a publication. Sure. Right? But it's only a failure if you didn't learn something from that process. So I can think of things that we did and spent a lot of time on that resulted in a failed grant or didn't lead to a high-profile publication, or we didn't even bother to write it up. But I don't consider any of those failures, because each one of those instances I could possibly list off we learned so much from that process that then contributed to the next thing that did result in a successful grant or publication. So no, I can't think of any. I would also say that I've also been very, very careful with how I spend my time to make sure that I'm spending my time on things that I think are important.
Yeah.
Explicitly, so I don't look back and say, wow, I never should have put my time into that. That was a failure. So yeah, the short answer is no. I really struggle to come up with anything that I sunk time into that I would say, nope, that was a total waste.
Yeah, sounds great. And do you have tips on how to do that for listeners? Because, I mean, how do you know what's going to turn out gold, right? I think one thing that struck me when I started as a postdoc with you was even you said something, you don't want to publish papers that don't change the field, which is, I think, it was new to me. I think it was super helpful to hear that, actually. Because you can't change the field with every paper, obviously, but having that ambition to do it in the first place is I think, a good one. Or any other tips or thoughts?
Yeah, it's a great question. I guess one is, how do you bias things in your favor? Because you're right, you don't know what's going to work and what's not going to work, right? Yeah. So one is you always want to have multiple horses in the race. So don't have one project, have 3 projects, and then spend your time based on which of those 3 projects looks like it's emerging as something truly important.
Yeah.
Maybe all 3 will, but usually not. Usually one of the 3. And so leverage your bets, right? Have multiple horses in the race. 2 is think about what the end outcome is if you're right? And I think that there are people that spend a whole lot of time proving something that's right that really doesn't move the needle, even though they sunk a few years into it. And so, in my case, our goal is translation. And so there's a lot of cool scientific questions out there, but if it's unclear how you're going to take that result and then translate it back or use it to eventually improve a therapy, I tend to put that as lower on my rank list as to where I spend the time. We don't publish a lot of the smaller papers that we could. It takes a really long time to publish even a small methodological point. And I'd rather just kind of mention that methodological point in the next bigger paper and spend the time on that rather than spend the time on lots of smaller methods papers that people may or may not see. And then the other one is you bias the results in your favor up front, but you're never going to get it right all the time, and you're always going to sink a lot of time into a project that didn't work. And then it's just making sure you capitalize on that experience and that time spent so it's not a failure, right? So, okay, you spent a huge amount of time on this project. It didn't result in something that is worth writing up, right? So what are you learning from that? Because if you didn't learn anything that you can take with you into your next project, it is a failure. But if you bias things up front in your favor and then you learn from every experience that you have, then there isn't really a failure.
Yeah, that sounds great. Yeah, that was another great piece of advice you gave me back then. Just saying that even the small papers take a lot of effort, right? So are they really worth your time, right? So hedging, like, from the many things you could do, I think you once formulated it in a way that was something like, there's always enough ideas, but being a good scientist means to choose the ones that will have the biggest impact, right? From the ones that you could work on. It was also super helpful for me. So,
and remember, some of the smaller papers too, someone else will do it.
Sure.
Right? And so it's also don't write the paper that people always worry about competition and am I going to be first and no, that's a great opportunity to relieve a time constraint. If someone else is going to do that paper and write it up and do a good job, then you don't have to.
Yeah.
And so that's another one is don't, like I said, don't join the herd. If somebody else is already doing it, let them do it.
Yeah.
Spend your time on something else, because doing the same thing they're already doing, that's not going to help the field.
Sure. Yeah.
Although,
some more replication is helpful, I think.
Oh, yes.
That is certainly also, that's also some advice one could give people that have, anxiety of being scooped, to say that usually both papers will be valuable or have some, right? But
no, that's a good point. That's good. I don't want to dissuade replication is really, really important. And actually, when I review papers, I am very positive on a well-done replication that either replicated or in some cases didn't replicate it. But either way, no, that is also very, very important.
Then zooming out further, like very general advice to the young people entering the field, why would they want to pick neuromodulation or let's say, or lesion network mapping, or why neuroscience at all in this time? Or do you have any advice how to choose your topic, or do you? I'm sure that if you went back and looked at interviews and recordings from the last 100 years, someone is at any given decade going to say this is the best time that you could ever go into neuroscience, right? Sure.
And they're all right. And the reason is the tools we have available to understand the brain and convert that understanding into neuroscience treatments gets better with each decade. So as time goes on, it's always the best time to go into neuroscience because we always have the best tools to actually do things. But no, I there's always a lot of poo-pooing of academia and I absolutely love my job. I love what I do. I get excited every day when I come to work and work with brilliant people. Now is a very awesome time to be in neuroscience. I would say that unlike people that said the same thing decades in the past, the tools we have available to us today allow us to go after symptoms that are in need of treatments with real optimism that we can rapidly translate that back into an improved DBS, stimulation setting or an improved TMS stimulation site. I think the path to translation has never been shorter. But we also, with those same tools, can address topics that are important to neuroscience, but also important to society outside of neuroscience. And the fact that we can go after things like free will, criminality, religion, is also a unique point in time where I don't know how you would have really studied those in a rigorous neuroscience manner without the tools we have available right now.
How will neuroscience look like in the future? What is coming?
What's coming for neuroscience in general? Geez, I would say a whole lot more human stuff. I'd say that we're now doing things directly in people, all the electrophysiology happening in humans that used to be only possible in rodents and monkeys. And so I think, the neuroscience of the future is going to be human neuroscience because we're going to have more tools for recording both invasively and non-invasively in human patients, more tools for modulating brain circuits in human patients. And so I do think the ability to directly do neuroscience in humans is really exploding. And I'm excited about it.
That's great. We talked about some missed opportunities, like, for example, recording serendipity, but do you think there are other things that we as a field, neuroscience or neuromodulation or neurology even, should be taking that we're not taking these days?
Yeah, beyond the topics we've already discussed, I would say the one that I've been thinking about lately is the gap between the animal science and the human stuff. And it's as I've started to wade into this, it has been very interesting to understand just how big that gap is, and how different the approach and motivation is when you're doing a rodent optogenetics experiment, right, versus the clinical problems that we're facing, and is that optogenetics experiment actually addressing a clinical problem, or is it just really cool, rigorous neuroscience? And I think there just needs to be more conversations. You have unique people like Carl Deseroth, who is a psychiatrist and a clinician, and it takes it back and forth. But I think that's the exception, not the rule. There's a lot of very, very good basic neuroscience happening with circuit manipulation in rodents that we haven't found a good way to translate or have a conversation with the clinical problems. And your opto-DBS approach is targeting that, but the opportunity there I think is big, but the gulf is very, very wide.
It's even just not clear if it's the same region we're talking about, right? So
you don't know if it's the same disease, same symptoms, same circuit, same region. Again, the gulf is so wide that a skeptic could say, okay, you're never going to be able to take anything in a rodent and translate that to anything useful in a person. And I don't fall on that extreme. But at the same time, I think that many people do end up on the opposite side, where they assume that this ginormous gulf doesn't exist, and that if you can have an effect on a symptom that kind of looks like a human symptom in a rodent, oh, well, gee, easy peasy, right? Just translate that optogenetics intervention to a circuit therapy in humans. And I think that you can't underestimate the size of that gulf.
Yeah.
Doesn't mean it's not possible to circumvent it, but it's massive. And so, I don't want to just discount all the very cool neuroscience happening in rodent models, but how we get there, there's a lot more steps involved that I think is commonly appreciated.
Makes sense. I want to be mindful of your time, and I would have tons of more questions. I want to stop with one last guest question by Fred Schaper for you.
Hiya, Mike. This is Fred, one of your postdocs. I got a question for you. Let's say Brigham says in 6 months, for some reason whatsoever, you can take a sabbatical, but the only thing you can do in that sabbatical is do a postdoc for 2 years. I'm curious, how would you decide where to go? Who would you work for? And what would you do in that postdoc? Thanks.
Oh, a great question.
I love it too.
Man, so I get to do a 2-year postdoc with anybody that I want. So...
And he wants to know how you choose.
Yeah,
where you'd go as well, but maybe what's the rationale why?
Yeah. So it's always you choose the smartest person doing the thing that you don't know how to do, but you'd benefit from learning how to do it. And at different points in my life, that was non-invasive brain stimulation or functional neuroimaging or deep brain stimulation. And so I guess the question is what is that thing that I need to know how to do better, and who could I learn it from? And I'd say the first thought that comes to mind is, who knows how to run a center across multiple departments better than I do, right? And there are certain names that come to mind, Helen Mayberg and others that have done this and launched these efforts, because that one's a challenge, right? And I mentioned before, you see where the herd's going and you intentionally do it differently, right? Well, I didn't become a division head, I didn't become a department chair, because I don't know how I would do it differently, right? Someone will do those jobs and they will do a very, very good job, and probably a better job than I would do. But going a different direction from the herd is building a center across multiple different departments that put different people together in different ways, with the idea that different things and thoughts and treatments might emerge from that. But it's very challenging. And so, I would almost consider an administrative postdoc of how you learn how to do this. And then I guess on the pure scientific side of things, it would probably be kind of on the circuit modulation from the animal model optogenetics side.
Oh, really?
Simply because there's so much happening there and so many smart people cranking out, I bet every week you open a Nature or Science journal, you're going to find at least one optogenetics study in there. And so, I almost feel like I must be missing something, right? There's really important science that's happening there that the scientific community that does more basic stuff is really pumped about.
Yeah.
And I know the human stuff really well, but that's an area where there are very, very good people that I think I could learn from to begin to understand, can you cross this gulf? Is it possible? And how would you even begin to approach it? And so I think that would also be really valuable.
Super cool. I love that. I'd love to see that. You at the bench with mice.
Oh boy! Gotta go back to my pipetting skills. I did do mouse research actually.
Oh, you did?
Yeah. No, I did. I did mouse research as an undergrad at Ohio State, and then I actually worked with Tom Woolsey at WashU, who did the barrel cortex. He discovered the barrel cortex in mice, and we had a whole set of experiments in imaging the barrel cortex and trying to understand when you stimulate a whisker, why does blood flow actually go up, and is it trying to wash out bad stuff? And so I did actually do mouse research before I ever did imaging research.
Interesting. Did not know that.
It just didn't take.
Anything you wanted to cover that I did not cover? I covered a lot, I guess, but
I think you know me well enough at this point to ask all the best questions. And no, this was a super enjoyable time, and so thank you so much for having me.
thank you so much once more. Thanks, Mike.